Hello, everybody. Welcome to this talk. It will be a real-world smart contract vulnerabilities. As Bea said, my name is Buendía, and I will be your speaker for the next 30 minutes. So this is a little bit the agenda that we are going to cover today. I will do a brief introduction about my background. I promise it will be brief. Later, I will go on talking about what we will cover in this session. And after that, I will go directly to the core of the talk, to the meat, to the vulnerabilities that we are going to see. We will do finally a summary with the things that we have learned, and in the end, a brief greeting section. So, introduction about me. We already say my name. I am a Solidity Smart Contract Auditor at Halborn. I have been a web application pen tester, a mobile application pen tester, a bounty hunter, and a security researcher enthusiast since a long time ago. So, about this talk. So, really good that Gabi did a small 101 before, because this is not going to be a 101. I am assuming that you already know how smart contracts in Solidity work. I am assuming already that you know the basic about blockchain. I will try to cover 3 different decentralized applications, one staking decentralized application, one DAO, and one lending and borrowing protocol. We will cover a total of 3 vulnerabilities, 3 exploitable vulnerabilities and 2 bugs that are not exploitable. And the aim is to explain a little bit most of the common architectures that you can find when auditing smart contracts and some of the most kind of iconic vulnerabilities in order to give an understanding of the mindset that you should take when dealing with audits. The target audience for this talk would be everybody that already knows the basics. So let's go to the meat, to the vulnerabilities. So as I said, the first decentralized application that we are going to cover is a staking application. So these applications mainly allows users to deposit their funds and give them rewards over time. This is a concept that it's already covered in classic finance, like your bank do when you deposit money for having interest over time. The particular in here is that that time is measured on the blocks of the network. Okay, there will be some pools that will handle all the liquidity that the users will deposit, and in a given block lifetime, they will distribute the rewards. So this was a kind of a centralized architecture because there was an administrator that could deploy the pools and change many of the parameters of the contracts. And in order to register the activities of the user, the application had a snapshot system, let's say it like that. It was just simple data structures that handle every time a user deposited or withdraw money within the pools, the liquidity pools, okay? So the main contracts were these 4. The router, there was just a contract placed in front of all the other contracts of the system for simplifying the communication with the protocol for the users. We also have the pool factory, that it will be a contract that will be deploying the pools that the administrator wanted to deploy. The pool contract, that it's the pool template itself, that it will handle the liquidity of the users, and it will be the one having the rewards and the lifetime measured in blocks. And also this application had a staking contract that it's actually not so much involved in here. So this is the first code vulnerable snippet that we are going to see today. So this function was placed on the router, and it's called the pay reward pool function. This function allows users to pay for buying a slot storage on a type pool payable. Okay. So basically, let's see first what this function is doing, and we will try to see later how to exploit it. So as you can see, this pool was receiving first 2 parameters, that it was an address type pool and a UIN256 amount. You can see on line 9 how it's calling this address to the function is payable and receiving a Boolean value. If this Boolean value was true, then we can go on with the execution. Later, it calls this get pool info that just takes an address of this data structure, the payment token, that is basically the address of the token that the pool accepts payments in. Later, what we are having from line 16 to line 21 is that the router is transferring the deposits from the user to the router. It needs to be previously approved for the user. And later, on line 27, you can see how the router is calling the pay function from the pool, where it's directly transferring the message sender, so the one that has called this transaction, and the amount specified by the user. This function is returning a UN256 value, that is the refund value. If this value is bigger than 0, then the router will give back the tokens that the pool did not accept to the users. We all understand what a refund is. So what's the problem in here? The problem is that anybody can supply an address pool to this contract, and if there are funds of that token in the contract, you can steal everything that is inside the router. So the basic idea in here is to assume a scenario where a user will accidentally deposit some ERC20 tokens on the router. This may sound a little bit complicated, but actually in Web3 happens more than it should. So the exploit code for exploiting this vulnerability is just deploying this evilpool.sol that allows you to set an ERC20 token. That is the one that we are assuming that the user accidentally deposit the tokens in the router. We also need this isPayable function that, as we saw previously, we need that it returns true. We need the getPoolInfo for returning all that data structure. And for the pay function, as we need that refund value, the only thing that we need to do is to answer with all the balance that the router has. So directly, when receiving this value, the router is going to transfer all the funds that it contains to us. So how to mitigate this vulnerability? Well, actually, in the pool factory, it was existing this function already, the isValidPool, that contained a data structure that had all the valid pools. This function was used in many places along the code, but actually in this application, in that concrete function, it was not being used. So it's as simple as that. They already knew it, and they actually forget it. So let's go on with the next two bugs. They are going to be in this same application. And these are non-exploitable bugs, okay? But they're interesting because they are simple mathematical bugs. The reward formula for the pool is this one that you can see in here. That is T sub 1 divided by the TVL multiplied by the rewards per block multiplied by the number of blocks. So as we said before, the pools have a life cycle measured in blocks, and they have a total number of rewards. First, let's start by studying what is this T1 divided by TVL. So this T sub 1 is the amount of tokens that the user has deposited, and the TVL would be the total value locked inside the pool. So let's assume that two users deposited 100 tokens each inside the pool. So the total value locked in the pool is 200 tokens, but what one user deposited is 100. So this simple division will give the 50% of amount of rewards that should be for me, and the other 50% of rewards that should be for user number 2. So for this scenario, I did a simple case knowing this formula. The rewards per block in here is the total rewards divided by the end block minus the start block. Okay, we assume that a pool has 1,000 tokens of rewards and have a 5-block lifetime. It's just as simple as divided 1,000 by 5, which gives a reward per block of 200 tokens. Okay, it's going to give 200 tokens each block. So I created this simple scenario where we have this pool with 1,000 token rewards, 5 blocks, and 2 different users. So before the pool starts, we are going to stake 100 tokens. So in the first block that the pool is going to distribute rewards, as it has 200 tokens for giving, it will be 100 for user 1 and 100 for user 2. The thing in my test case scenario is that in block number 1, user 2 deposits another 100 tokens. So basically, if we do now the maths, the 66% of the rewards should go for user number 2, and 33% should go to user number 1. So this is 133 tokens for user number 2 and 66 tokens for user number 1. I know there is 1% missing, but don't be nerds. So in the end, they should finish with this number of rewards. So user number 2 with 633 tokens and user number 1 with 366. But what was really happening? The thing was that if we saw the test execution, we would see that user number 2 on the second block didn't receive any rewards. And actually, at the end of the execution, user number 1, instead of having 366 tokens, it was having 400, and user number 2, instead of 633, it was having 500 tokens. So we have a really small discrepancy in here that is actually not serious for a business that is handling money. So what I did was print the execution, and I also printed these snapshots that I was talking about before, that are the data structure that is registering the execution of the users, to see what was happening. So these are the snapshots for user 2. As it's taken 100 tokens on block number 46, from block number 47 to block number 50, it will have 200 staked tokens, okay? So going a little bit deep into the code of the reward distribution, more or less you can directly forget about what is in here. I just put this for you to understand this calculate reward function. The thing starts in here. In here we take the snapshots of the users, and we start to iterate through them in order to calculate the rewards for each user. The problem is on line number 29. If you see in here, we are subtracting the end block minus the start block. Okay, and if we go back, if we subtract 50 minus 45, it's going to be the 5-block lifetime that the pool actually has. But if we subtract 46 minus 45, we have 1. And if we subtract 50 minus 47, we have 3. So rewards for user 2 is actually calculated for 4 blocks instead of 5. So it's actually possible to infer that the pool is missing a block every time a user stakes or withdraw tokens during the lifetime of a pool. So now let's go to the bug number 2 that is also in this same snippet of code. I don't know if you realized it, but the rewards per block, we already discussed that it was going to be 200. But if we sum the numbers that we had previously, we are seeing that the pool is distributing, instead of 200 tokens, 213 tokens. So it's distributing actually more rewards than it should. The problem is in here, it's in the code that we saw before, that is that the pool is calculating an average between the start TVL and the end TVL. And for user number 2, that doesn't represent a problem, because in the first tranche is doing 200, the average of 200 and 200 is 200, and the average of 300 is 300. But for user number 1 that didn't stake or withdraw anything, the start TVL is 200 and the end TVL is 300. So the pool is assuming that for this user, the TVL is 250 tokens. And as the TVL in the formula, it's inversely proportional to the result of the rewards, we are having an improper reward calculation per block. This created many situations where users were not even able to withdraw tokens from the pool, as the amount of rewards that they were wanting to get was bigger than the rewards that the pool actually has. So the transaction was reverting all the times. So how to mitigate these bugs? As you can see, this was more or less a design flaw. And basically, it took the developers several months because they needed to rewrite the whole reward system distribution. So let's go to the application number 2. Let's talk about a DAO, okay? First of all, before going any further, the vulnerability I'm going to explain is from Roberto Reigada. He's one of the best Solidity smart contract auditors I have met. And well, let's go to explain what he found. So a decentralized autonomous organization, it's a set of smart contracts that allow users to create proposals and to vote for or against them. So in order to create kind of a feeling of democracy in the DeFi ecosystem, okay? We have this executor address that every time that a proposal gets voted, a proposal in the end is just going to be to execute a function of a concrete smart contract. So there is always this executor address that it's going to be the contract responsible for executing what the DAO decides to execute. So how do users vote? Users don't have one vote, each of them. In here, the voting power is decided for the money that you put inside the decentralized application. So normally, all the application has a standard token, an ERC20 token, and they have also a staking token where you place that first ERC20 that we were talking about, and that amount, it's going to be your voting power that you're going to be able later to use inside the governance contract. So what was the vulnerable code in this DAO? So first of all, looking to this staking.sol, this would just be the staking token ERC20. So it has two functions, the enter function and the leave function. So as you can see, for getting voting power, you just need the balance of the standard token of the system, and it's going to mint you the supplies that correspond to that amount. And directly, you are getting the voting power you're going to be able later to use in the governance contract. And also, for taking back your tokens and giving back this voting power, you just have this leave function. So there is no time restriction at all, and you just get your tokens back. And in order to vote, as you can see on line number 3, the only thing that we are doing is taking the balance of the staking smart contract directly. So what Roberto thought in here, that it was kind of a really nice idea. So if I can create a malicious proposal for changing the executor contract address for me in order to have the control of the DAO, of course, if I create that proposal, users are going to vote against it directly. It's not gonna go any farther. But after 3 days passed in this DAO, if you have enough voting power, you could approve the proposal and actually execute it directly. So Roberto thought that also with a flash loan at the end, we could vote for the proposal, execute it, get our token backs, and repay back the flash loan all in one single transaction. It's going to be 2 flash loans, one for creating the proposal and the other one for changing the permissions of the DAO. So this is a little bit, this is a struct of the exploit contract. For those of you who doesn't know, this is the standard function that whenever you ask to a flash loan for Uniswap, the contract of Uniswap, it's going to call back to this function in your address that is the one that is going to receive the funds. Well, I didn't specify it, but I hope that everybody knows what a flash loan is. In the end, a flash loan is it's a mechanism that allows you to have a huge amount of cryptocurrency for a single transaction, with the only exception that you need to give it back at the end, or it will revert and not persist on the blockchain state. So all these lines are just for taking the variables that we are going to need. And this if-else is actually the core contract, the core code of the exploit. So this part of the if0 is for creating the proposal. We will create a proposal with the target address of this. So for changing the executor address to the contract that we control, we will endorse the proposal, we will activate it, and then we will leave the staking contract, and we will repay back the flash loan. In the second transaction, what we are going to do in here is vote for the proposal, execute the proposal, reclaim the votes, all in one single transaction, and repay back our flash loan. So this was a super nice attack. And how do you mitigate this? Actually, this is a pretty standard thing on DAOs. You need to add a time constraint every time that you are giving voting power to a user. You cannot give voting power directly, because if not, you're having these kind of issues where a single user asking for a huge amount of money can change the voting power in just one transaction. So finally, let's go to the third vulnerability. This vulnerability is from Alejandro Taibo, also known as Kaorth. He could come here and explain it probably better than me, but I think he's too comfortable in there, so let's not bother him. So this vulnerability was on a lending and borrowing protocol. How do lending and borrowing protocols work? Well, this is more or less easy. Basically, lending and borrowing protocols allows you to deposit a collateral in order to ask for a loan against the collateral that you deposited. So for example, imagine I am able to deposit 1,000 euros in order to receive $1,000, but without changing my 1,000 euros. If I am not able to repay those dollar bucks, my euros are taken from the deposit in order to repay what I took. So in this protocol, what was given as collateral was an NFT. For example, imagine a Bored Ape that cost a lot of money. So you can deposit as collateral in order to take other kind of cryptocurrency. So the simplified version of this, because this was a quite messy protocol itself, is that you were depositing your NFT in a delegation wallet. This delegation wallet was a set of smart contract based on top of Gnosis Safe that had a guard contract to kind of blacklist or check that this NFT that was deposited in here was not possible to be removed. So now, what is the worst case scenario that you can have on this protocol that I'm describing here? Well, basically the worst scenario is what Alejandro found, that is that you deposit an NFT, you take a loan, and you take back your NFT, so you don't need to repay anything, and you go with borrowed money. So the vulnerability resides basically in these two sections of the code. This executor.sol that was on the part of Gnosis Safe contract that basically allow to execute a delegate call to an arbitrary address indicated by the user. And in the guard.sol, we're able to see that it's not checking at any point if we are using this enum operation of type delegate call. So for those of you who don't know it, a delegate call, the only thing that it's doing, it's executing the code of other contract in the context of my contract. So basically, the exploit for this is to modify the address of the Gnosis Safe in order not to point to any guard contract that is going to blacklist us from transferring that NFT out. So the storage slot in which the guard contract was stored in Gnosis Safe was at this slot. This was possible to be taken actually directly from the source code of the contract. So the only thing that this exploit is doing is storing the address that we are receiving as parameter in this slot. So the proof of concept, this is a test in Foundry, is just locking the NFT in the delegation guard. We can print the value of the storage, and later executing the transaction in order to call our guardian manipulator contract that we defined in here. So later, the guardian address get modified in the storage, and we can actually transfer our NFT from the delegation wallet. So Alejandro found also other 3 ways of bypassing this, but in half an hour I just have time for explaining this one. But basically, the easiest way for preventing this is just blocking that enum operation delegation call. So to summarize, we have seen the first vulnerability that was a lack of input sanitation. That's a classic. It happens in web, it happens in mobile, it happens in smart contract, it's going to happen in everywhere. For the second bug, when dealing with a smart contract, please do always check the maths. You're going to have a white paper, you're going to have a documentation. Check that the formula that they are saying that in order to distribute or handle the funds of the people are actually what it's actually doing what it's supposed to do. The second one, when dealing with DAOs, always be aware of the time when giving voting power to users, because if not, as I have shown today here, it's possible to manipulate it with a flash loan. In lending and borrowing protocols, beware always what is happening to the collateral that the user is depositing. If not, he can run away with a loan, free loan. And as you can see, all the things that we have talked about are about funds, how the funds are distributed, how the funds for the user move, how the contract is handling the funds itself. So when dealing with a smart contract, please check how the currencies are being dealt with. Finally, little greetings. So thanks for Carlos Polov for inviting me here to talk. Thanks to all Harbonauts for building every day a more secure DeFi ecosystem. Special thanks to Gokber Gulgun, to Roberto Reigada, and to Alejandro Taibo for being the best mates I could possibly ask for. Thanks to Redline Team and Licor de Bellota, and finally, to my family. That's all.
That was amazing, Luis. Thank you very much for coming here. It's very, very awesome to see some real Web3 vulnerabilities that our team has found and has prevented from being exploited. We are running a little bit out of time, so let's have one question. Do we have any question here? No. So let me ask just one question to you. What do you think in your experience, because you have been looking for vulnerabilities for several years now in the DeFi world, in Web3, what do you think is the current situation? Do you think we are going to be having a lot of other vulnerabilities where people are going to be stealing millions, or do you think that we are the environment is getting more and more mature and these things hopefully won't be happening?
The environment is getting more mature, but we need more people like Gabby to build more security from the blue team perspective, and we need more adoption of auditors to try to prevent things from happening.
Will you recommend the people in this room to get started doing Web3 security?
Totally.
Yeah.
It's fun.
Cool. Well, thank you very much, Luis.